so I
You
have
only
to
have
wash
one?
it. Yes, I only have one.
Really?
One bandana?
I
Well,
mean,
I've got a
it's
bunch of Nike ones, but then it looks like I'm trying to be Roger Federer all the time. I don't
I'm
want
trying
you.
to be who?
Roger Federer?
So you're saying is we need to, as a group, buy you more headbands?
Yeah.
Count me out.
Count Jesse out.
Wait,
Yeah,
when's
I
your
already gave
birthday?
him my old ones. What's my birthday? December 29.
September?
December.
Oh. I don't know.
Okay. What's up, man?
I'm just testing the strength and material of this chair.
Uh-huh. A little ADHD going on today, is that,
No, I'm
The
good.
hair, it's not pulled back, it's not
that's
bubbles.
right, that's right. It's too distracting. All right, I'm bringing in a clipper, I think.
Oh.
You know, I'll tell you what, how about this? How about this? You get less than an A, I get to shave your head. You get an A, you get to shave my head. How about that?
I would cut my hair for bonus points.
As in at the end of the semester, he's not getting an A, he'll let you cut his hair for an A.
Oh, I see how.
Oh, that's a good idea.
Yeah,
cut my hair.
it's on video. We don't want to commit to any kind of.
Have you
Brian,
started,
it's on
it
camera.
yet?
All right. Yes, it started. All right. It was just a joke. In case anybody's watching, it's just a joke. All right. So
We'll talk.
we have a whole course about material, a whole course on material science that describes the details of the nuances of how materials respond to these shear stresses and shear strains and normal stresses and normal strains. But we're not going to cover that in this class. We're just going to have a one lecture summary of the entirety of chapter 3, which is sort of itself a summary of material science. Okay. So for those of you who've had material science before, feel free to nap. If you remember, yes, I'm on it. If you remember, that is what we're talking about, material science. Otherwise, for those of you who haven't had it, we'll go through the brief discussion now, and you'll have it in earnest the whole semester next fall. Okay, so
We get to that during the whole semester next fall, then, right?
what's that?
We get to nap the whole semester next fall, right? It's like
Yeah,
community
sure,
property.
sure, because yeah, in material science. Yeah. So you just show up and take naps. Yeah. All right. Okay, so everything I'm going to give you now, just sort of take as a given. It's a description of the way stress strain behavior happens, and then again we'll talk about it more later. So there's an interaction. Oh, I forgot to put the thing up. The problem up between stress and strain. Okay. Normally this is characterized in a one-dimensional tensile test, where we take an object and in its most simple form, we pull on it and measure how it strains. Okay, so we know we have this known applied stress, we measure the strain, and we plot the two. We would plot the applied stress and the resulting strain on a stress strain diagram. Now there are two ways that we can characterize stress and strain. We use engineering stress and strain, which is what we really are going to use most of the time. In that case, stress is the load divided by the initial cross-sectional area. So we measure the cross-sectional area once, we start applying the load, constantly dividing that load by the cross-sectional area. And then the strain is the change in length, or the elongation, divided by the initial length, whichever set of terminology you want to use. So again, we measure the initial length, usually between 2 points on the specimen. We don't measure the entire length of the specimen, because in most cases the specimen is actually not a nice uniform cylinder. We usually have some kind of a thicker section at the top and bottom in order to concentrate the stress just in the center. So we have a large area at the top so that it doesn't deform, Then we have just the small area in the center where all the deformation occurs. And then we'll measure the initial length of this section. So that's the engineering stress and strain. And the reason it's called the engineering is because it's practical. We measure the initial quantities and then we pull on it. And everything's normalized by those initial quantities. What's called true stress and strain are normalized by the instantaneous quantities of area and actually, let me not draw the strain up there because I don't think we want to. The strain's actually an integral. You have to integrate delta L as L changes. So it's the integral of dl over L as you integrate strain. But the point is, you don't use the initial conditions, you use the final conditions. The only reason we distinguish between these two is because the graph that I'm about to draw for the stress strain diagram is different for engineering and true stress. Okay. So engineering stress, this is easier to work with in theory. If you're doing like a finite element thing or something where you're measuring the area all along, theoretically, this is better to measure in experiment, in practice. Because it's very difficult once this thing starts to stretch to monitor how much it has already stretched, or to monitor how it has shrunken in cross-section. You're talking about the silly putty. Pull on silly putty, it necks down. You have to keep monitoring that area constantly. It's a lot easier just to use the initial conditions. Okay, stress versus strain. So I'm going to draw this in a way that is really somewhat exaggerated. The scale is not going to be right. So I'll draw first. Okay, this section here is usually very compressed against the horizontal, vertical axis, and the elongation out here is much broader. But I've sort of zoomed in order to show you the points I'm interested in. So there are several points: point A, point B, point C, point D, and point E. A, B, C, D, E. Now this is the curve you would get for a mild steel, for instance. If I used aluminum, aluminum would look more like this. Again, scales off because the aluminum wouldn't be as strong as the steel. Okay, but the general shape of the aluminum curve doesn't have these extra features in it that the steel one does. Okay, so, and on the aluminum, just put the labels on the aluminum points. C doesn't exist. B would be there, D would be there, and E would be there.
What's the super basic reason for that, or is it just really complicated?
I'll explain it in a second.
Okay.
Well, I'll explain the super complicated part next year. I'll explain what they are in just a second. Okay, so point A is called the proportional limit. It turns out that no matter what you're using, engineering stress and strain or true stress or stress and strain, the curve is pretty much the same all the way up through point A or B, depending on, essentially through point B. Okay, both engineering and true stress are the same through point B. Okay. And in this region, from the origin to A, it's a straight line. It's a linear behavior, a proportional behavior, right, which is a line going through the origin, a proportional line. So that stress is equal to Young's modulus, or sometimes the elastic modulus, times strain. E is a constant, a material property, capital E. And it is the slope of this linear region. So, that's the proportional limit. So up, you can go up and down, and that's all elastic, meaning it's recoverable. You go up, you go down. You go up, you go down. Okay, that's where we like to use materials, where we get the same behavior every time. You pull it back and forth, and it keeps going back and up. Okay. Point B is the the elastic limit or the upper yield point. So the point is, between A and B, it's no longer linear. But between point A and B, it is still considered to behave elastically. In other words, you can recover, remember elastic collisions, right, from UFIS? So there's no loss of energy in the velocity. What's that?
It's like a rubber band.
Like a rubber band, right. But between A and B, it's no longer linear. Okay. On the mild steel curve, blue one, we call B the upper yield point. Yield is the point where it starts to deform. So B is the point where deformation starts to occur in the case of a mild steel. Okay. But the upper yield point doesn't mean anything in the context of the aluminum curve because it doesn't have an upper and lower. So B would just become the yield point on aluminum. And I'll explain a little bit in detail in a minute, excuse me, how we determine where B is. I mean, it's easy to determine where B is in the mild steel, right? It's the peak of that little hump. On the aluminum, it's a little more difficult, so we have a method. C then, when it exists, is the lower yield point. Lower yield point. D is the ultimate tensile strength. And E is the failure strength. The point at which it breaks, fractures. Sometimes called the fracture strength. So those are all the different points. C doesn't exist on aluminum, but all the other ones do. Okay. In the case of aluminum, the way that we determine where point B is we extrapolate back a line at a slope of E. So we extrapolate a line straight back from B. And when this value is 0.002, that's where B is. B is defined as the 0.2% offset. So in the case of aluminum, B is the 0.2% offset yield point.
Just on aluminum? Or
Well, on anything that behaves like that. So anything that's not a mild steel.
like a soft, any soft.
So copper would behave that way, nickel would behave that way. So the mild steel has this extra little hiccup in it. But it's important to know because mild steel is what most steel structures are made from. A big steel I-beam is made typically from mild steel. So that's why it's important to know. But most materials just follow the red curve. And so we consider it to have yielded when the extrapolated line is 0.2%, or 0.002, strained in 0.002. Okay, so that's what engineering stress and strain looks like. True stress and strain, come up here and do something like this. So we'll call this the green line, and the engineering stress and strain are the blue line, and the red. Okay. So, first thing you notice on this graph, the D, the ultimate tensile strength, that says that the stress goes down after you get to that point. You yield to a certain point, it stretches, right? This is all elongation over here, yield. So the things, the coat hanger that you're pulling on now is beginning to stretch. So it stretches up to a point, and then it says the stress actually goes down inside the component. But what's really happening is that from D to E, the cross-sectional area is reducing, is necking, so much faster than the increase in the ability to hold additional stress. Since the true stress strain curve compensates for the instantaneous area, it recognizes the stress continues to go up until failure. because it knows, it calculates, oh, there's a smaller cross-sectional area, so my stress is actually going up faster than my load is going down. But from D to E, my load-bearing capacity is going down because the cross-sectional area is shrinking so fast, even though the stress is going up. Does that make sense? Okay. So that's why the engineering stress strain is particularly useful, because this is the maximum load I can bear in that part. But that's 1,000 pounds, if that corresponds to 1,000 pounds, right? Because it's all based on the initial cross-sectional area. So if I know I've got a 1 inch, or I should, yeah, 1 inch square part, 1 square inch cross-sectional area, and it's bearing 1,000 pounds, I got 1,000 psi. If that's 1,000 psi, then I know I can't put more than 1,000 pounds in this thing. Whereas on the green curve, I can't really tell what I can put on it or not, because I don't really know, there's no clear definition of the maximum load, because I don't know how it's going to neck. I don't know how it's going to the cross-sectional area is going to reduce. So D, is the ultimate tensile strength, is really useful from an engineering perspective. Yeah.
But you don't want to go all the way up to D, right? Because
No, you don't want to,
the
but that's
plastic-
sort of the ceiling. I know it's going to break after that.
Right, okay.
Okay. So the engineering curve is just much more useful in terms of actual application, because I don't care about how it's necking. All I care about is what load is it holding. That's all that matters. Right? I design a component. I design it based on a particular load. We talked about this earlier last week or the week before. We design around a load. Then say, okay, well, what cross-sectional area, how big of a bolt do I need to withstand that load? Right? If that bolt narrows during use, I don't care. It's got to hold that load. Right? That's the key parameter. The cross-sectional area of the bolt is typically not the thing I'm designing around. It's the load that's holding. Okay. So that's why the engineering stress strain curve is more useful typically. But like I said, up into this section here, they're pretty much the same. In fact, what's interesting is that the elastic modulus, the E, the capital E there, is pretty much the same for a particular material, no matter how it has been treated. Well, we'll come back to that. We'll come back. I need to introduce a few more terms first, I think. Okay, so let's talk about some terms based on this graph. The first is ductility. Ductility is essentially the deformability. How much can you deform the material? And it's measured as percent elongation either at yield or at failure. So percent elongation at failure. So where would percent elongation at failure be? It would be this point, the horizontal axis corresponding to that failure point. Right? So this value right there is the ductility, is a measure of ductility. An alternative and less used is percent reduction in cross-sectional area. So percent elongation we already defined. That's just the strain and failure. Percent reduction in cross-sectional area would just be A minus A naught divided by A naught, instead of L minus L naught divided by L naught. So either one of them, but typically the percent elongation failure is the way you characterize that. So the more it stretches before breaking, the more ductile it is. Okay. If I had a piece of glass, it would break up in here. Glass doesn't stretch. Right? So it has very low ductility. Piece of copper, going to stretch much better. Right? Piece of rubber, very stretchy. Right? Okay. Brittleness is kind of the other end of the spectrum from ductile. Sometimes brittle materials have no yielding. You pull them up this straight line, and they break before they even get to B. Now it turns out low yielding typically occurs at the atomic level, but very little. Okay. And there are some materials that can be both brittle and ductile depending on where you work. Anybody ever do the liquid nitrogen experiment with a banana? Or a rose petal? You ever know? No? Ever seen this done? You dunk a rose into liquid nitrogen. You pull it out and you drop it on the table and it shatters into a bazillion pieces. You ever seen this? Okay. So, what's that? What'd you say?
Terminator,
Terminator? They did that in Terminator?
kind of.
I'm trying to remember.
It's like the second one.
All metal dude.
Yeah,
Oh, the metal dude.
the metal dude.
The metal dude.
The guy that's like liquid metal all the time.
Yeah, yeah. So anyway, so the point is, if you change the temperature, steel behaves the same way. Steel will be nice and ductile, but if you get it too cold, steel becomes very brittle. Okay, so temperature effects can change ductility, between brittle and ductile behavior. And there are other things. You can alloy, you can change the way the alloying constituents and take something that would otherwise be ductile and make it brittle, or more brittle. Okay, by putting a few percent of some other contaminant ion in there. Okay, so we've got the elastic modules. Again, as I said, for engineering and true stress, both follow essentially the same curve. The difference between them is like less than 0.1%. Okay, less than a 1 in 1,000 difference between the elastic modulus for true stress and the elastic modulus for engineering stress because there's so little necking that occurs in that section. Most of the necking occurs when you actually deform something. Okay. And as I say, if you change minor composition, so if this is a low carbon steel and maybe I gradually tweak the amount of carbon in the steel, so it's steel, you guys know steel is iron and carbon predominantly. So if I have a mixture of iron and carbon and the amount of carbon is less than 1%, or something around 1% carbon, the rest of it's iron. Is here. If I change the percent carbon, the slope of this line will be the same, but the yield point might come up here, or it might occur down here as I change the amount of carbon. But the slope of that line will typically remain essentially the same. Okay, so the elastic modulus doesn't really change for a particular material for a particular material type. What changes is the yield point. The point along there where it begins to deform. And that's to a first approximation. Okay, another concept, strain hardening. So a hard material requires more stress to deform it. A soft material requires less stress to deform it. Does that make sense? Right, so if I've got silly putty and a rock, right, it takes very little stress to deform the silly putty, but it takes quite a bit of stress to deform the rock. Because the rock is hard and silly putty is soft. So strain hardening is the idea that once I go up this curve and actually go past this, and let's say I stopped at this point, right? So I've deformed the thing, I've stretched it out. Then if I unload it at that point, take the load back off, it will again extrapolate down along a line of slope E. And when I get back to no load, it will have some residual strain. Does that make sense? Right, it'll be stretched, yeah.
And then if we do the same tensile test again, will we get the same curve, or?
We do the same tensile test again, we go up the same curve we came down. So now our yield point is higher than it was before. We've made it harder. Okay, so that's the strain hardening. That make sense? So in other words, that's why you can never bend a hanger back. I say this because assuming everybody knows metal hangers, but anymore it's hard to find metal hangers. But you know what I'm talking about, right? Or your metal ruler or any other piece of metal. I bend it, oh man, I gotta bend it back. I can never bend it back. Because the point where it's been bent is up here. Right? The bent point has been deformed. I try to bend it back, it's gonna deform at a part that hasn't been bent because it's easier to deform there rather than at the point where it's already been bent because I can't. You see what I'm saying?
Yeah.
The other stuff is softer. So that's why you can never straighten it back out again. Right? And the only way to straighten it back out is to somehow force your stress to be concentrated at the point that you're trying to do it. So that's why you hold it really close to the point where you bend it to try to get it back. Does that make sense? Okay. Common life. We all know this stuff. We're just putting a little bit of science behind it. Okay. That's strain hardening. Strain energy. How do I measure energy? You guys know physics. How do I calculate the energy that I'm putting into something? What do I call it when I put energy into something?
Work.
Work. See, I almost said whoop. Work. So I do work. So how do I calculate work? Come on. It's an easy one. Physics. How do I calculate work? Work is give you a hint. It's the integral. It's an integral. And even without the
Force
integral.
in time.
Force and something. Force, yes, it's force.
Distance.
Force and distance. Right? It's a force acting through a distance. F dot dl or F dot dx. Right? Remember that now? So, what happens if I want to calculate instead the work per unit volume? Well, that's going to be the integral of F dot dl over volume is area times length. Right?
Is it still a dot product or is it?
It's still the dot product on top, yeah. In the most basic sense, it is. Okay, but in this case, we're uniaxial, so dot product doesn't really mean anything, because everything's a line. Okay. So, what is F over A? What is stress, right? Oh, you guys are really struggling with the grade lab class. What's DL over L? This side of the room. Sorry, Kayla already answered the first part. This side of the room. You guys sit over here by yourselves. They have to answer half, you have to answer half. That's the way it works. What's DL over L? It's on the stinking board already, guys. Strain. It's actually D epsilon, right? Because I'm using DL instead of delta, right? So it'd be D epsilon.
So derivative of strain.
The derivative, the incremental derivative of strain, right? Because we're going to integrate that.
So strain at point.
So, right, straight in a point. So if we integrate it, it's just stress times strain. You know, because if we represent them as initial area and initial length, then the area and the L come out. You see what I'm saying? And we just have to integrate the displacement or the stretch. We integrate the stretch. The integral of d epsilon is just the integral of dl because we're dividing by L0, which is just L, or delta L. Okay, so, but that integral, right, this is a linear function, right? Stress is equal to E times epsilon. So that's the integral of E epsilon d epsilon, right? So then the work per unit volume is equal to 1/2 E epsilon squared, or 1/2 sigma times epsilon. Or, if I want to put it in terms of just sigma, 1/2 sigma squared over E. As long as we stay in the linear regime. The assumption we made here is that we're in the linear regime. Sigma equals E times epsilon. So up to the yield point, or the proportional limit anyway, up to the proportional limit, up to point A, the strain energy, the energy we put into this thing, in deforming it. Right? Calculated one of those three ways, depending on which one you want. And graphically represented here, let's go to black. One color I haven't used yet. Graphically represented here as the area in that triangle. So, the bigger the area in the triangle, the more strain energy, the more energy it takes to cause the part to yield. Okay? So, if we're just trying to get to yield, the strain energy at yield we call that the modulus of resilience. So a material which has a large area under this graph is highly resilient. It can take a large load and experience a large deformation and still come back, wash after wash. Old commercial from the 70s. Okay, but it will still come back to its original condition because it's all elastic. It's essentially the amount of energy it can absorb elastically without undergoing any kind of plastic deformation. You guys remember elastic and plastic collisions? Elastic and plastic deformation, same idea. Elastic deformation is deformation where the energy can be regained, where you have conservation of energy. You get the energy back up. Okay, modulus of resilience. The strain energy at failure we call that the modulus of toughness, or sometimes just the toughness. So where would that be? The area underneath the whole curve, right? So I come down here, right? That's going to be, let's see here. I guess we'll do it this way. All that area. That is the toughness. So a tough material is one that in the process of deforming can take either a large load or a large amount of deformation. So glass is not very tough because glass can take an incredibly large load but has very little deformation. So you end up with a tall, narrow region, small area. Rubber is not very tough because rubber can experience a huge amount of deformation but can't hold much load. So you end up with a long, narrow section this way. But steel, not as elastic as rubber, not as strong as glass, but it has a large area because it has a pretty high load and a pretty long deformation. Does that make sense? So toughness is measured by how much you can take before you break. Now last time, Colin, Blake, one of you guys, asked about what happens when it breaks.
Yes, I did.
You did? Okay. So when it breaks, what's going to happen? Well, it's going to break in two, right? This thing's going to break in two. But each of those two pieces, once it's broken, will relax back. So what essentially happens is some of that energy that has been absorbed is released back as those two pieces come back. This is the energy that gives rise to the sound from breaking. Okay.
Because that's really loud, it's way louder than I thought it'd be.
Yeah, but it doesn't take much energy to make a lot of noise. right? I mean, think about it, your eardrum will rupture at 1 watt per square centimeter, or per square meter, right? That's the amount of acoustic energy that your body can withstand before it, before it experiences pain. I don't know if it'll rupture, but anyway, you'll have damage. The threshold of hearing at the top end is 1 watt per square meter. Okay? That's 1 watt's like very small power. So it doesn't take much energy to make a lot of noise. Especially when you put it in this context. Okay? All right. One last thing to define then, after strain energy, is Poisson's ratio.
Is that first strain energy, is that at the linear, in the linear spectrum?
So strain energy, everything is accurate up to here. This is universally true up to this point. Here's where I plugged in the linear section. E times epsilon, right? That's just holds in the linear section.
Okay.
Slope times, that's the proportionality.
Right.
So from here over, we're talking about just the linear section. Okay. Strain energy is still the area under the curve. It's just we don't have a good way of calculating it beyond the yield point, beyond the proportional limit. Okay. So we can calculate the elastic strain energy pretty straightforwardly. The plastic strain energy is much more complicated to calculate. Okay. All right. Does that answer your question? Last thing, Poisson's ratio. This has to do with the fact that even when we pull on it in the vertical direction, there are still dimensional changes in the lateral dimension. It's the necking that we were talking about, right? So Poisson's ratio is defined, it's nu, the symbol nu is used for Poisson's ratio. It's defined as minus the strain in the lateral direction divided by the strain in the longitudinal direction. So if on our diagram over here, we call this the z direction, and the lateral dimensions are x and y, right? Then this would be equal to minus the strain in the x direction divided by the strain in the z direction, and it would be equal to minus the strain in the y direction over the strain in the z direction. So y and z for a homogeneous material, uniform chunk of aluminum, the y and z behavior is going to be the same. Now, if the specimen does not have a square cross-section, if it has a rectangular cross-section, the deformation in the y and x directions are going to be different, but the strain will be the same. The ratio of the deformation to the initial dimension in each of those directions. Okay, how do we feel about that? Just quickly try to pull the thing up for, I've done this before.
So if you smash glass with a hammer, is that considered a deformation?
Yeah. So anything that changes the condition of the material. Changes the, anything that changes the shape of the material is considered a deformation. Or changes the volume. Anything changes that. Some of it's recoverable, so if it's an elastic deformation, I pull on it like a rubber band, and then I let go and it goes right back to where it was. It's still, it doesn't have any net deformation because it went back. It was elastic. Seriously? Oh, it's sleeping, my bad. Come on, there it goes. Do we have a homework assignment due
Wednesday.
Wednesday? Okay, that's the first one, right?
60%, right?
Yes, you only have to do 60%. Well, you know,
You
I
didn't-
encourage you to do all of them.
Yeah.
What is it doing on Wednesday? Is it do it Wednesday at midnight, or is it do Wednesday at like
Class period.
Class period?
Is this chapter 3 we're in? Is this in chapter 3?
You
No,
said
yeah,
you're doing
316.
chapter 3 today?
This is 3, right? Why am I not getting? That's weird. Did I go in statics? Yep, I went in statics. That's why. Okay, wait a second. That's not it. Okay, there we go. So let's do the first one at least. So the guy sitting on a beam, supported by a wire. I'm guessing Dr. Davis must have had quite a lecture earlier, because there's a lot of schmutz in this board.
Was it Davis or Kears?
Well, Davis had 2 lectures and Kears had 1, so.
Oh.
Okay.
Dr. Davis was never really good.
Oh, there's nothing you can do about it. I mean, it gets
He
schmutzy.
normally brings in cleaning
Oh,
stuff.
well,
Yeah.
oh. That's very conscientious of him. Okay. So we got this guy sitting on a beam supported by a wire. The wire is diameter 5 millimeters, made from A36 steel. This is why we bring our book. So we look up properties of various steels
Look at that.
in the index. And this A36 steel.
I don't think it's here. Then comes extra fine.
Where is it then?
Here's what's extra 2020.
I wasn't able to carry my book.
I'm trying to find the properties. Beams.
The information on my shoulders.
Must be in the chapter. I don't know. Oh, maybe it's in the back here. Aluminum, steel. A36, bang, right there, inside the back cover. A36 steel. What do I do? Where do I start, Blake?
Free body.
Free body diagram. All right, what free body diagram of what? What are we gonna do a free body diagram of, Blake? Hey, gave you the low hanging fruit, now you gotta back it up with a little something.
Of DE, or I guess, yeah, let's do DE.
Of DE?
Yeah.
Free body diagram of DE?
No, let's go ABC.
A, B, C. It's as easy as 1, 2, 3. All right. I'm gonna go with ABC, I like that better. A, B, C. Okay. And why we call D and B coincident points, I don't know, but, okay. So what are the loads that are acting on this ABC bar?
We have a force W point C straight down.
Okay. We got a force W here. Equals what?
8 times 9.8.
80 times 9.8.
9.81, whatever.
Okay, so what is 80 times 9.81? We'll just leave it as 80 times 9.81 so we move on. Okay, what else we got? What other forces on ABC?
We have a reaction force in the X and Y direction on A.
Okay, so we have a reaction force here and a reaction force there. AY, AX.
With force in the direction of BT.
In the direction of what?
ED.
In the direction of E, I should say. Okay, and do we know anything about that force?
We don't have be in just this direction.
Which is direction? Here's the way I'm going to represent that. It's a 3, 4, 5 triangle. Okay? So, three-body diagram. We got a font. What are we trying to solve for? FDE, right? The force in DE. So, best approach to doing that?
Moments about A.
Moments about A. All right, so this stuff should be very straightforward. We should be able to get through this much faster. Some of the moments about A. What are the moments about A?
0.8 times the DE in the y direction.
Yeah, I should put the dimensions on here. 0.8 meters and 0.6 meters. Okay, so it's 0.8 times. What am I going to write up there? Who said the force in the y direction? Okay, you can be more specific than that.
Yeah, let's see.
Just look at the picture. Don't use your calculator.
Whatever the angle is.
That's what I'm saying. We don't need the angle. It's a 3, 4, 5 triangle. So 0.8 times 3/5
Alright.
of FDE. Right? See what I'm saying? Because FDE is the 5, so it's 3 of the 5 that are pointing vertical. Okay. All right. Is that positive or negative? That moment. Positive. Okay. What about this one? What about the next moment? It's going to be negative. What's its value?
784.8.
I don't think that's it yet. We don't have a moment. That's a force, not a moment. What's the moment?
Oh, yeah, sorry.
Times 1.4.
Yeah, 1098.
Right, that's fine.
Yeah, sorry.
Okay. So now we can solve for FDE because all that equals
0.
0. We get FDE is equal to 2289. Hopefully, because that's what I got in my paper. Okay. Is that what we need? What are we trying to find?
Elongation of the wire.
The elongation of the wire. Is that the elongation of the wire? No, we're not there yet. So what do we need? Hmm?
So stress in the modulus.
Right, so really, we're looking for, we know this equation. We know stress and strain are related in this way. I can rewrite that as force divided by A naught is equal to E times delta L over L naught, which is my preferred nomenclature for writing strain. What is it I'm trying to solve for? Delta L. So delta L is equal to F times L naught divided by A naught times E. Do I know F?
Yes.
Do I know L naught?
It's a meter.
It's a meter, right? 3, 4, 5 triangle. Do I know A naught? Well, it's 5 over 4 d squared, right? Because they give me the diameter. And do I know E? I can look up E. E in the book. A36. Modulus elasticity, 29.0. You'll notice that for all the 4 steels alloys listed, they're 29, 29, 28, 29. Again, showing that the modulus is fairly consistent for all of them. 29.0 times, oh wait, this is in KSI, sorry. The metric table's down below. 200 gigapascal. So that's equal to 2289 newtons times L naught, which is 1 meter, divided by pi over 4 times 0.005 squared, it's 5 millimeters, right? Yeah. Times 200 times 10 to the 9th. And I plug all that in, and I get a delta L of hopefully 0.583 times 10 to the minus 3. That make sense? Sure. You look like you might not be convinced then. You're okay. All right. 351, so if you're not convinced, you'll have to convince yourself. So I got responses from 3 people about Gmail addresses.
Blake doesn't do computers.
Blake does.
I saw your email, but I don't have your email.
So if you want to be able to watch the videos offline, I need Gmail, otherwise
Oh, Jen, outside there.
you're not losing anything, you're not able to watch the
Can
videos.
we, oh, yeah.
And I will post,
I can't quote.
once I get all the links, once I get all the videos uploaded.
I just remember, that was just,
To have
that's,
them if you want.
for some reason, that's what I thought of
We're
when
gonna
he was
make
talking
one and
about.
say
You
you're.
can never go,
this and that.
yeah, and these be led, I was like, that's, it just
That's
came
all.
out of my head.
Folks,
Faults? I got something from Williams.
Williams, that's Colin.
Oh,
Good
sorry.
evening.
Right, sorry. Sorry.
No, that's fine.
Williams, Wheeler, yeah. That would be.
Yeah.
But, so,
I
it,
understand you're right, first name, right?
yeah,
Blake Williams, right? I know Blake Williams.
Yeah, that's the other senior, or one of the
Oh, the
seniors
guy from last year,
Yeah.
that's it, yeah, okay. See, that's what, okay, so it's all in there somewhere.
yeah,
No, you're-
Okay, so yeah, you just make them on Google, just go on Google and make a
yeah,
address, but that's just, the only reason to do it is if you want to be able to watch these offline.
okay, but it, like, if we were to want to be able to watch, we don't have to have it done within a certain time period, do we?
As soon as you give it to me, then I will